we're looking at the second class test, the unassessed class test today. Now, you didn't quite beat last year. Last year, about a third of the class turned up for the unassessed class test. So when I said you didn't beat them on attendance, because only 30% of the people turned up this year. We had 63. Well, actually, a pretty close run thing, really. However, you did do much better than they did on the actual test. But on the other hand, I did set a rather hard second-class test last year, so it's not easy to tell. But still, I was rather pleased with how you did, because you averaged, those who turned up to the second-class test averaged just over 70%. So that's pretty good. And last year, well, the average was a lot lower than that, I can tell you. Now, some of these questions you found very easy, so we won't have to spend too long on them. So if we go through the boring bump at the middle, let's see. I'll do something slightly bigger than that. Let's see if we can fit in 150%. Just about. Okay. So, the first question, I can tell you that 98.4% of the answers were correct, so we shouldn't have to spend very long on this. So the correct answer is A12, and there were 98.4% of you were correct. Remembering the highest common factor is always going to be a positive factor. So it's got to be positive. So you've got really a choice between 12, 18, and none of the above. And since 60 is not divisible by 18, you've got a choice between 12 and none of the above. But the correct answer is 12. So I don't think I'll spend any more time on that, unless anybody's got any questions as to why the highest common factor is 12. If you do have any questions about that, you might want to contact me. Okay, so I'll move on from there to question 2. Which, if any of these statements, is true for all integers? Let's have a look. 93.7% correct, so not quite as large a percentage, but still most people getting this one right. Okay, so let's just run through these. The moment. It has to be true for all integers. Interestingly, this is different for all real. It's different if you ask for all real numbers, when it would be none of the above. Okay. So if I said which of these is true for all real numbers, then it would have been none of the above. But because it's integers, D turns out to be true. So we'll have a look at that and see why. But first, let's just check why the other ones aren't true. Obviously, true for all integers. It's unlikely that m squared will always be equal to m. So, for example, 2 squared is not equal to 2. It's also not true that m squared is always not equal to m. For example, 1 squared equals 1. So these are both wrong. M cubed greater or equal to m works for positive integers and for 0, but and even for -1, but it starts to go wrong after that. So this one is wrong, for example, e.g. -2 cubed is smaller than -2. And this one is true, but you might want to do a case-by-case analysis for m smaller or equal to 0, m squared is greater or equal to 0, which is greater or equal to m. So D holds. And for m in Z, with m greater than 0, we have m is greater or equal to 1. And that's where it's different between integers and real numbers. If you have an integer that's greater than 0, then it actually has to be greater or equal to 1. And so, well, details of m squared greater or equal to m. You could write m squared minus m equals m times m minus 1. And you can see that that's a product of two non-negative things, because m is greater than 0, m minus 1 is greater or equal to 0, so that's greater or equal to 0. Okay, so that one is correct. But as I say, it would be different from real numbers. But since almost everybody got it right, you must have figured that out. Okay. So let's move on to the first of the tricky questions. Now, 58.7% got this one right. And the correct answer is C. Okay, these are statements with two quantifiers, and these take a bit of getting used to. So you need to figure out what these things mean. Okay, now the way to figure out what a two quantifier statement means is normally to put a bracket round the easier bit with just one quantifier and figure out what that means. Now, this will be a statement. Y, in here, you can figure y as a dummy variable if you're regarding this as a statement that x might satisfy. Okay? So you have to think of this as something that x might satisfy. For all y in q, y squared equals x. Well, it's unlikely that x is going to satisfy that, because that's saying that the square of every rational number is the same, equal to x. So this is no way going to be true. Even if x... I mean, whatever x is, this is going to fail, because all you have to do is try two different y's with two different squares, and they can't both be equal to x. So if you let, so for A, if you let x be a natural number, then the statement all y in Q, we have y squared equals x, says that all rational numbers y have the same square namely x. And this is, I'll say, clearly ridiculous, but you can... So this is clearly false. Well, at least it's clearly false to me, as I said. And I'd accept that it's clearly false. If you wanted to justify it, you would probably just give two different y's whose squares are different and say, well, they can't both be x. And so no matter what x you try, this is going to fail. So that one is wrong. Okay. The second one is slightly different, but so for B, let's try and figure out what that one means. This time we'll let y be in Q. By the way, the only time that something ridiculous like this could be true is if the first bit was something like for all x or for all y in the empty set or something like that. That's the only time that one of these things could actually turn out to be true. If the inner statement is clearly ridiculous, it can still turn out that the whole thing is okay if you begin with something vacuous like for all z in the empty set or something, because then things turn out to be true after all. Okay, but we're not dealing with the empty set here, so if the inner statement is completely ridiculous, then the whole thing is going to be completely ridiculous. So here's another one. This one, this time, the inner statement is going to be completely ridiculous because it's saying that for all natural numbers x, x is the same with x equal to y squared. I still need to have that. Let's see. Then, for all x in n, y squared equals x, says that all natural numbers are the same and are equal to y squared. And this is clearly nonsense as well, okay? Again, the only way for the whole statement to be true here was if it had been for all y in the empty set or something like that, in which case this would have been a true statement, but for stupid reasons. We're not doing anything like that. Okay, so now, I think this is a bit too big. Let's make it a bit smaller. It's about the first time in this module that the tablet has lost the pen. You used to do this quite regularly. Now, the way, I'll just pause the recording while I sort that one out. It is a computer. Okay, so that worked. So in case anybody else has a problem with losing their tablet pen, this system still works where I flip the screen and then flip it back again, and then it finds the pen again. It's better than restarting. Right, okay. Let's see what is the difference between C and D. Oh, thank you for that, yes. Okay, so yes, let's see what the difference between C and D is. C is the one that's true and D is the one that's false. D says that for every natural number and every rational number, the square of the rational number is equal to the natural number. So we can give a counterexample to that by choosing, we could do the interpretation that says clearly false, but we could just give a counterexample to that by choosing a natural number and choosing a rational number where it goes wrong. So the nice thing about a for all and a for all statement is that you can do it just with one counterexample of one of each. Because this is for all x, for all y, we can disprove this with one counterexample of each. If it was an exists for all y, then the counterexample y would have to be in terms of x. And if it was a for all x exists y, then you'd only need one x, but you'd have to prove that your counterexample worked. So let's see what counterexample should we use. Well, we just have to choose any natural number and any rational number where the square of the rational number isn't the natural number. So that's false. E.g., x equals 1 and y equals 2, the counterexample. The other ones, which were exist x such that for all y, or exist y such that for all x, you couldn't have done that with a counterexample of one of each. You couldn't have said, for example, x equals 1, y equals 2. That wouldn't have been convincing because there might have been a different x that would have worked. So you really have to show that no x works, but the statement about y was so ridiculous that I regard it as obvious. And again, for B, you really need to show that there is no y that works. You can't just say, for example, y equals 1, x equals 3, even though that pair doesn't work. The exist means you have to show that none of the first things are available that will make it work. Whereas, because this one's a for all x and a for all y, for all x, you want to disprove the for all x, you just need to find one x where the statement is going to go wrong. And for that x, to show it goes wrong, you only need to find one y to show that for all y goes wrong. So you really do only need one pair this time. So that's what's friendly about a false for all x, for all y statement, is that it makes the counterexample particularly friendly. I haven't explained C yet, but any questions so far about the false ones? Yes. Oh, what have I done there? Oh, yes. Thank you very much, yes. So I want a counterexample. I want an example where y squared is equal to x. Thank you. So it was a particularly friendly one for finding a counterexample, and I got it wrong. Okay. It tells you that I should have read my own statement. Thanks for that. Yes, so this shows that you can have a pair x and y where y squared is equal to x. Therefore, the for all x and for all y, they're different, was wrong. Thanks for pointing that out. Okay, so what's going on with C? Well, again, I'll put a bracket round the middle thing. If you take an x in the natural numbers, you have to figure out what this statement about x means. This one says, for all y and q, y squared is not equal to x. What that says is that x is irrational. The square root of x is irrational. Okay? Because if the square root of x was rational, then there would be a rational number whose square was equal to x. And if the square root of x is irrational, then there isn't a rational number y, so that y squared is equal to x. So this inner statement here says that the square root of x is irrational. So the question is, does there exist an x in the natural numbers so that the square root of x is irrational? And the answer is yes. So this time you prove it true by example, and the example is 2, for example. I mean, or many others. So C is true. For example, you take x equals 2. Then square root of x is irrational. And so for all, what was it, y and q, was it a y and q? Yeah, for all y and q, y squared not equal to x. Because if y squared was equal to x, then the square root of x would be rational. And as I said, any other natural number x where the square root of x is irrational will do. So this is proved true by example, and that's because it was an exist x statement. So the only things you can prove true by example are the exist statements. You can't prove a for all statement true by example unless you're dealing with a set with only one element, or some very small number of elements where you can check case by case. Okay, now that I think we've got that right, any more questions about this one? Okay, thank you. Let's move on to the next question. Question 4. 82.5% got this one right. And the correct answer is A. So I won't say too much about this. Let's see. Y take away x equals empty set. This one says this one is equivalent to saying that y is a subset of x, which is the wrong way around. We want it to imply that x is a subset of y. This one is the same as saying that y is a subset of x. X intersection y empty suggests that they probably got nothing to do with each other. It doesn't quite stop x being a subset of y, because x could be the empty set, but it almost does. And A and B, one of them's the right way around and one of them's the wrong way around. A says x take away z empty. That's if and only if x is a subset of z. And if x is a subset of z, z is certainly a subset of q, and if you know that q is a subset of y, then you're home. X will be a subset of y. Then y has to contain x because y's got all the rational numbers in particular, y's got all the integers in. So you could say you've got x is a subset of z, which is a subset of q, which is a subset of y, and so x is a subset of y. And B, it's slightly wrong. B, x take away q being empty means that x is a subset of q, and then you've got z as a subset of y, means y's got all the integers in, and x is a subset of the rationals, but since a half might be in x, and a half might not be in y, you could give a specific counterexample. So, for example, counterexample to B, for example, is x equals q, y equals z, and then everything holds, but x is not a subset of y. So the condition holds, but x is not a subset of y. So this one, it isn't true that if B holds that x has to be a subset of y, because you've got a counterexample. There are plenty of other counterexamples as well. Any questions about this one? Okay, so let's move on to another tricky question, and this is the one that people found hardest. 47.6% correct on this one. Now, this may be important because it's something that people have got wrong in the exam every year as to somehow people are finding this one difficult. Now, I suspect that what made this one difficult is that I flipped x and y in the true statement, that you probably found it confusing that I flipped x and y, but there's no reason to use any particular names for your variables. So let's see what's going on. Which of them is true for all functions? Well, what's true for all functions is that for every element of the domain, there's a unique element of the codomain which is equal to its function value. Okay? So if I do that in words, so the true statement for all functions f from R to R, we have the following. For every element, and I'll use a different letter, A, of the domain of f, which is R. Okay, which is R. There is a unique B in the codomain, which is R again, with B equals f of A. If it's a genuine function, it's only allowed to take one value at A, whichever A in the domain you take. Now, it doesn't matter whether you call these things A and B, W and Z, X and Y, or Y and X, as long as you remember which one's where. I mean, there are other statements that are true about all functions, but the one we're looking for is for everything in the domain, there's a unique thing in the codomain where f of the thing in the domain is the right value, and that's D. So for every real number, y, the value of f of y is unique. Okay? You're not allowed to have more than one value f of y. Otherwise, it's not genuinely a function. So now you use y instead of a, and x instead of b, and you use math symbols. So it's for all y in the domain, there exists a unique x in the codomain, which is R again, such that f of y equals x. But you can do it with a and b instead if you like, and you can swap x and y and it becomes another true statement, which is one that probably looks more familiar to you. Okay, so all the other ones are wrong, but let's see what they actually say. So A, for all y in R, there exists an x in R such that f of x equals y. What does that one tell you about the function? Yes? It maps to everything in the codomain. So what, it does hit everything in the codomain. So what's the name for that condition? Surjective. That's the one where f is surjective. So this one says, assuming it is a function, this says f is surjective. All y in R, there's a unique x in R such that f of x equals y. Who could tell me what that one would tell you about the function? Yeah? So you're going for injective. Any other?
It's a
One-to-one. Oh, that's the same as injective. But it does say for all x in R, there's a unique y in R such that f of y equals x. So it's a bit better. Any more? Yes? Bijective is the one, this one. So this is the one that says that bijective, oh, sorry, where have I got to? B, this is the one that says that so that's for, so this time, because we're looking at f of x equals y, this time this is a for all y in the codomain, there's a unique x in the domain with f of x equals y. That says you're bijective. Let's have a look at statement C. This time it says for all x in R, there's a unique y in R with f of y equals x. But I've just swapped x and y over by the look of it. I don't remember that I planned to do that, but it seems that I've just swapped x and y in B, so that this means the same thing as B, so it says that f is bijective again. I'm sure I didn't have that. I didn't mean to do that. This also says that f is bijective. X and y, you can swap x and y here freely because it's all, and it makes no difference to the statement. So I've got one that says it's surjective, two that say it's bijective, and one that says it's a function. So, any questions about that one? I do think this is an important one because I think people get a bit confused about injective, surjective, bijective, and so that's obviously a bit that one of the bits that people find hard. So I think people should think about that. Something always comes up about it on the exam. I can't tell you what's going to come up, but you really do need to understand functions and their properties if you don't want to cut yourself off from some bits of the exam. So any questions about that one, which was probably the question you found hardest? Well, if not now, think about it, and you can always come back with questions about it on Friday, or you can send me emails, whatever. Okay, so we'll move on from there. Looks like I was mistaken to think that we were going to finish early. We have to carry on with this on Friday. Okay, so here's another chance to recognise the definition of surjective. But this time, 69.8% got it right. Now, the question only said which of them implies that G is surjective, but in fact, I gave you a condition that was equivalent to being surjective. I didn't have to, but I did. So let's try and recognise what some of these things mean. The correct one is B. So this you should interpret as for all S in the codomain, there's a unique T, there exists not a unique one, there exists at least one thing in the domain which hits it. So that exists T, so that G of T equals S, tells you can get at every different S in R. So this is the one that says you're surjective. A is true for all functions. For all T in R, exists S in R such that S equals G of T. That says for all T in R, G of T is a real number. So this one's true. Again, even without the uniqueness, it's still true for all functions. Exists S in R such that for all T in R, S equals G of T. What does that one say? What does that mean about the function? Yeah, so it's a constant function, right? This one says it's a constant function. For some real number S, everything gets sent to S. So this one says, this says the function is constant. And constant certainly does not imply surjective in this setting. In fact, implies it isn't surjective. So that's definitely bad. And D, there exists an S and T in R, says that S is not T, but G of S equals G of T. What does that one say about the function?
It's a many-to-one function.
A many-to-one function, or in other words, it's not injective, okay? So it's a perfectly possible thing. This one says that the function is not injective. But not injective, in no way does not injective imply that you're surjective. Of course, if you wanted to demonstrate that not injective didn't imply surjective, you would give an example. I won't bother giving you a counterexample, but just think of your, again, take a constant function will do. Constant functions here, not injective, but are definitely not surjective either. So, e.g., if G is constant, G satisfies this but is not surjective. Okay, let's have a look at the next one. Question 7, I thought might cause some trouble, but 82.5% of people got it right. So the correct answer is 33. Now, 10 to the 330 is a rather big number. However, if you subtract 1 from it, you do get 339s in a row. And you could work from that. So there are 330 of these. And you could work from that, or you could use modular arithmetic. So to figure out what the highest common factor is here, you would probably factorize 330, and you'll see that that's 33 times 11 times 2 times 5. And you have to figure out how many of these factors go into 10 to the power 330 minus 1. Well, you can see that 3 does, or you can use modular arithmetic. You can see that 11 does because there's an even number of 9s. If there's an odd number of 9s, that wouldn't work. So that gives you the 3 and 11. This is clearly odd, so it's not divisible by 2. And it's clearly not divisible by 5 because it doesn't end in a 5 and a 0. But what I'll do is I'll probably come back and say a bit more about that on Friday. Okay, so we'll finish off our discussion of the class test. We got as far as question 7 last time, and I gave you a sort of brief description of one approach of it. I just want to say a little bit about the modular arithmetic approach. So yes, we'd factorised 330 as 3 times 11 times 2 times 5, so that's the prime factorisation. So those are the only primes that can be involved in the highest common factor, and they can't go to any higher powers than are shown here. And so what you have to do is look at 10 to the power 330 minus 1 and try and decide which of these primes do go into that. And I did say one approach is to write it as 339s in a row, but the other is, as I say, to use modular arithmetic. So let's see how we would do that. Well, 10 is congruent to 1 mod 3. So 10 to the power 330 is still congruent to 1 mod 3. So that's 1 to the 330, which is still 1. And so if you subtract 1, so that quickly tells you that 10 to the power 330 minus 1 is divisible by 3. Which you can write as 3 divides 10 to the power 330 minus 1. Okay. Then you have to think about 2, 5, and 11. 2 and 5 are pretty easy. I mean, 10 is congruent to 0, mod 2, and mod 5. So 10 to the 330 is still congruent to 0. Mod 2 and mod 5. And 10 to the power 330 minus 1 is congruent to minus 1, which is not congruent to 0, mod 2 and mod 5. And that'll do for that, I think. And finally, you have to deal with 11. 10 is congruent to minus 1 mod 11. So 10 to the power 330 is congruent to minus 1 to the power 330, which is 1 mod 11. So 10 to the power 330 minus 1 is congruent to 0 mod 11, telling you that 11 goes into 10 to the power 330 minus 1. Okay. Ten to the power 330 minus 1 is divisible by 11. And the rest is however you want to finish it off. Okay. So that's why you end up with the highest common factor being 33. Any questions about any of these versions of showing that the highest common factor is 33? Right. Okay, let's move on to question 8. A union of half-open intervals. And the correct answer turns out to be an open interval from 4 to 12. And let's try and see why that is. Well, it's a union of infinitely many sets. So you can't directly sketch the whole thing, but at least you can give yourself some idea of what's going on by looking at what the first few sets are. So consider the first few of these sets. How about calling them, let's give this a name, set AN equal 4 plus 2 over n up to 9 plus 3 over n. So A1, that's when n equals 1. That's, so 2 over n is 2, 3 over n is 3, and you get the half of an interval from 6 up to 12 as the first of these intervals. The next one And I'll sketch these on a number in line in a minute. The second one, n equals 2, so 2 over n is 1. That means you're going from 5 up to 9 plus 3 over 2, so that's 9 up to 10 to the half. Say that again, 5 up to 10 to the half. A3, so that's 4 plus 2/3 going up to 9 plus 1, so that's 4 2/3 going up to 10. Okay, so let's have a look at some of these on the number line and see if we can see what's happening. I won't go through a full rigorous formal proof because we did one like that in lectures, which you can reconstruct. So it looks like all the action is happening between 4 and 12. Perhaps I shouldn't have done it like that. Let's see, 4, 8, 12, 6, 10. Okay, that should get us started, I guess. We might need 5. I'll put in 11. All right, okay. So A1 goes from 6 up to 12 inclusive. So here's A1 goes from 6 inclusive up to 12 exclusive. So there's A1. A2 goes from 5 up to 10.5 in a similar way. A3 goes from 4 2/3. So let's put a line under that. Goes from 4 2/3 up to 10 in a similar way. So here's A3. Maybe I should have used different colours. But anyway, now, you never quite get to 4. 4 isn't in any of these sets. So you never get to anything below 4. And you never quite get to 4, but you can get as close to 4 as you like. So you get everything that's to the right of 4 will be in one of these eventually, whereas 4 itself isn't in any of them. Now, when you take the union, you're looking at the stuff that's in at least one of these sets. So you draw all of these on the number line, and you take the union, you get the lot. So you definitely get everything from 12 down to 6 just because of the first set, and then you get down a bit further because of the second set, you get down to 5, and then the third set takes you down to 4 2/3 or whatever it is, and then, was it 4 2/3? Is that right? Or, let's see if I've got that right. Yeah, that's right. Okay, so okay, so the union gives you everything strictly to the right of 4 and strictly to the left of 12. And all of those things will be in at least one of these intervals. It doesn't matter how many of them they're in, as long as they're in at least one. So all x in 4, 12 are in at least one of these intervals. And you can check that, make sure you check that exercise, no other x are. X smaller or equal to 4 or x greater or equal to 12 implies x is not in any of the intervals. And so the correct answer is the open interval 4, 12. Anybody need to see more details of this one? Or are you... Anybody want to see some more details, or are you happy you could formalise that if you needed to? You okay? Okay, well, if you do have any more questions about that, let me know. I can't remember the percentage. I put it on, I announced it by email, the percentages, you got everything right. I think most people got this one right. It is a none of the above for once. Of course, you might have got none of the above without working out what the correct answer is. So I will just try and work out the correct answer for you. So we're using the binomial theorem here. And we want the coefficient of x cubed, x plus 3 to the 8th. And here's one way of doing the binomial theorem. So it starts with x to the 8th. Oh, no, x cubed I wanted. So let's start with... so we'll start with 3 to the 8th times x to the 0 plus 8 times 3 to the 7th times x to the 1 plus 8 times 7 over 2 times 3 to the 6th times x squared plus 8 times 7 times 6 over 2 times 3 times 3 to the 5th times x cubed, and so on. And we've got to the term we want here. This is the coefficient of x cubed. It's going to be 8 times 7 times 6 over 2 times 3 times 3 to the 5th. Which is close to some of the others, but it comes out as 56 times 3 to the 5th. So it's not quite any of them. So it's a none of the above. Any questions about that way of using the binomial theorem, or where I got those coefficients from? Okay, I'll assume that you're happy to use binomial theorem that way. You can always practice, and we'll move on to question 2. Now this one, I think it was only about 55% got it right, so I think that maybe not everyone remembered what squares modulo 13 were. So the idea here is let m be in the integers, what can n squared be congruent to mod 13? Well, if m is congruent to n, then m squared is congruent to n squared. So there's no point trying more than one version of, if you get two things that are congruent, you only have to try one of them, squaring it. It's not going to change what you get. Also, n squared is congruent to minus n squared. Well, it's equal to minus n squared, so it's only congruent to it. So that also saves you some time. So we only have to check naught, 1, 2, up to 6. The reason for that is 7 is the same as minus 6. 8 is the same as minus 5, which is the same, and so when you square it, it's the same as squaring 5. 9 is the same as minus 4, because 7 is congruent to minus 6, 8 is congruent to minus 5, and so on. All other integers will give you repeats of when you start squaring them. Squared, of course. So we'll square these and see what remainders you get. Well, the first ones are obvious. 0 squared equals 0, 1 squared equals 1, 2 squared equals 4, and 3 squared equals 9. 4 squared equals 16 is congruent to 3, mod 13. 5 squared equals 25, which basically I recognise as minus 1 mod 13. But you probably want to turn that into a 12. Um, 6 squared, 36, which I think of as minus 3, but you probably want to recognise that as 10. You do not have to put in the minus 1 and the minus 3. You can recognise that 25 is 12 mod 13 and that 36 is 10 mod 13, and save yourself one little bit. But sometimes it's helpful to spot the minus a small number. Can be useful sometimes. Okay, and everything else is a repeat. So we found all the squares. The squares modular 13 are 0, 1, 4, 9, 3, 12, and 10. So looking back at the ones listed, 3, 10, and 12 did turn up, but 8 didn't. So 8 is not a square modular 13. So in other words, the statement that's true is that for all integers n squared is not congruent to 8 mod 13, no matter which integer you try. Any questions as to why we only used 0 up to 6 and didn't try any of the other infinitely many integers? Or are people happy that we've now, that all the other integers will give you repeats of the ones we've done? If you try 13,000,003, that's just the same as 3. So you might as well have squared 3 rather than 13,000,003, and so on. Okay, that's the sort of reason. Okay, I think, any more questions about that class test? If not, we'll stop that one there. I'll stop the recording.